Today and tomorrow we're going to finish this portion of the course by talking about one of the quintessential applications of the work that we have done on second order differential equations, which is the idea of spring mass systems. Spring mass systems are, generally speaking, second order differential equations with constant coefficients. They might be either homogeneous or non-homogeneous, depending on the precise spring mass system that you're working with. Today we'll focus on spring mass systems which are represented by homogeneous ODEs, and tomorrow we'll talk about some slightly more complicated spring mass systems which are represented by non-homogeneous ODEs. Now, when you're working with a spring, one of the fundamental laws that governs the behavior of a spring is Hooke's law. Hooke's law gives you a relationship between the magnitude of a force which is applied to a spring and to the amount by which that spring is either compressed or elongated. Now, when we say that the magnitude of the force applied to the spring is proportional to the amount by which the spring is either stretched or compressed compared to its equilibrium state, resting state, that means that the force is equal to some constant multiplied by the amount of displacement. That constant, here represented by the variable k, is called the spring constant, and it is a measure of how stretchy / how rigid your spring is. For example, suppose that we have the following information. We have a regular old spring, but when we attach a 2-pound weight to the spring, then the spring is stretched 6 inches from its normal resting state. Based on that data, let's find the spring constant. So in this case, the force which we applied to the spring is the weight force of the object. The weight force, which here is given in the units of 2 pounds. As a result, the spring stretched by an amount that's equal to 6 inches. So using Hooke's law, F is equal to K multiplied by S, since the weight force is 2 and the stretch is 6 inches, then the K would be equal to 2 divided by 6 in the units of pounds over inches. So to determine the spring constant for a spring, just attach a weight to the spring and compare the weight that you attached to the amount by which the spring was elongated. Now, when you attach a weight to a spring, that can be done in a variety of different environments. You can do it, for example, in a medium such as air or even in liquid, where the medium is exerting a force of friction on the spring, a damping force. Or you can attach the mass to a spring in a vacuum, where there is no medium imposing forces like friction on the spring mass system. In free, undamped motion, we assume that the mass is attached to the spring in a vacuum. We are assuming that there are no forces like friction which are resisting the mass's movement. When we say free, undamped motion, we also assume that after some initial time, when the spring mass system is first set in motion, there are no additional external forces such as an engine or a piston which is driving the spring mass system's movement. Now, when you have a spring mass system and you're assuming free undamped motion, if the spring has spring constant K and the mass has mass M, then the position of the mass on the spring mass system can be modeled with a second order differential equation. It's usually represented by x double prime plus omega squared x equals 0. X is the object's position as measured against time, with the understanding that x equals 0 would be the object's position when it's sort of idly hanging from the spring. Now, what is this quantity omega squared? Omega squared is just shorthand for spring constant k divided by the mass. So the differential equation written above would be equivalent to x double prime plus k over m times x is equal to 0. For an exercise, let's consider the case of a mass with a weight of 2 pounds that stretches a spring by 6 inches. So at the initial time t equals 0, someone takes hold of this mass, pulls it down 3 inches below its normal equilibrium position, and then releases it, pushing it upward at an upward velocity of 2 feet per second. So let's use this data to determine the equation of motion. So let's assume that the spring mass system is in free undamped motion, so that it can be represented by the differential equation x double prime plus spring constant divided by mass times x is equal to 0. Now at the initial time t equals 0, the object has been pulled down to a location which is 3 inches below the equilibrium position. So I might represent this by a negative 3 inches, negative 3 to represent below, underneath the equilibrium position. The initial upward velocity, so the derivative of position at time 0, the object is initially moving upward, so positive 2 feet per second. Now right away, I can see a potential issue with the quantities that I have been given, which is that some of the quantities are given in terms of inches and some of the quantities are given in terms of feet. I need to make sure that the units of the length measurements are consistent, or I'll run into problems later on in the calculation. So I'm just going to go ahead and put everything into units of feet. So negative 3 inches, I'll convert to negative 0.25 feet. Now I have the object's initial position and its initial velocity. Committing to units of feet, I'm also going to convert this information in the first paragraph, first line, not 6 inches, but 0.5 feet. So now I need to determine the values of k and of m. So to find the spring constant, we can use Hooke's law, and this information given to me about what is the relationship between the weight force applied to the spring and the amount by which the spring was stretched out. The weight force, the weight of the mass, is 2 pounds, and the associated amount of stretch was half a foot. So if I put that data into Hooke's law, then I find that k for this problem is going to be equal to 4 in these units of pounds and feet. The last thing that I need to fill in the differential equation is to determine the mass. Now be careful, because the mass of an object is not the same thing as the weight of the object. The weight of an object is equal to the mass multiplied by the acceleration of gravity, which is represented by the letter g. Now G has different values depending on the units that you're using. If you're working in metric units, the units of G, the value of G is about 9.5. But in the imperial units of this problem, the value of G is 32. So plugging in the weight of 2 pounds and the acceleration of gravity in imperial units, then we can get the mass of the object in the corresponding units. The mass is equal to 1/16. So now that I've got the value of K from Hooke's law, and I got the mass by dividing the weight by the acceleration of gravity, I can finish filling in all the blanks of this initial value problem, and I can solve for X. We have a second order differential equation which is homogeneous, which has constant coefficients. So I can guess a solution of exponential form. And if I make that guess, I get the auxiliary equation r squared plus 64 equals 0. So r squared equals negative 64. So r is equal to plus or minus 8 times I. C1 cosine plus C2 sine. And now we need to determine the values of C1 and C2 using our initial conditions. Let me go ahead and calculate the derivative. And plug in 0 to both of these two functions. So if I plug 0 into x of t, then the sine term vanishes and I'm left with C1. If I plug 0 into x prime of t, the sine term vanishes again and I'm left with 8C2. So this implies that C1 is equal to negative 1/4 and C2 is equal to positive 1/4. And therefore the object's position at any given time is given by negative 1/4 cosine 8 times t plus 1/4 sine 8 times t. So the object's position is going to oscillate over time. And this makes some sense. If we attach an object to a spring and we pull the object down and then release the object, then the object is going to bob up and down, up and down.
The period of the motion is the time required for one oscillation. Boom, boom, boom. So it's the time between booms.
And without an external force like friction or some other damping force to slow the object over time, then this model predicts that it will keep oscillating and bobbing up and down, basically forevermore. Now we know that that's not necessarily realistic, at least not in many Earth applications. In most Earth applications, there are damping forces like friction, like air resistance, that would cause the object to return to a resting state after enough time. And when we're dealing with damping forces, the forces are proportional to the velocity of the object. The damping force is equal to some constant, which is usually called negative beta, multiplied by the object's velocity, which is the first derivative of its position. So spring mass systems where friction is being accounted for can also be represented by higher order differential equations. The only difference really is that instead of just having x double prime and k over m times x, we have a third term which sort of accounts for the damping force. And the third term is given by plus beta over m x prime, where m is the mass, x prime is the velocity, and beta is the constant that relates the size of the damping force to the object's instantaneous velocity. And we're going to make the assumption that beta is going to be a positive constant. All the constants in this equation, beta, m, k, are all going to be assumed to be positive. So in this case, we have a 1 kilogram mass attached to a spring whose constant is given by 16 newtons per meter. So the mass of the object is 1 kilogram. The spring constant is 16. The entire spring mass system is submerged in a liquid that imports a damping force which is numerically equal to 10 times the velocity. What this sentence is telling you is the value of beta. The damping force in magnitude is equal to 10 times the velocity, so that means that we're going to use a value of beta equals 10 in our differential equation. So determine the equation of motion if the mass is initially released from rest from a point 1 meter below the equilibrium position. So what this is telling you when it says the object is released from rest is that the object's initial velocity is being assumed to be 0. The object is not moving at the moment that it is released. At what position was the object released? It was released from a position 1 meter below equilibrium. So I'm going to record that as x of 0, initial position, equals -1, -1 for below. So with these values of m, k, and beta, we can fill in the blanks of our differential equation. The second derivative of the object's position plus 10 divided by 1, beta divided by the mass, first derivative, plus k divided by the mass, no derivatives, is equal to 0. This is the mathematical problem that we're going to need to solve. We have a homogeneous differential equation with constant coefficients, so I'm going to guess an exponential solution, and that gives me the auxiliary equation r squared plus 10r plus 16 equals 0. That factors as plus 2 plus 8, and so I get the two r values, r equals -2 and r equals -8. So our solution has the form number e to the -2t plus number e to the -8t, and that's x, not y. Now let's go ahead and calculate the derivative of this quantity, since we'll need it to plug in the initial conditions. And if we plug in 0 to the function and to its derivative, the object was released from rest, so its initial velocity was 0. Its initial position was 1 meter below equilibrium. And if I plug in 0, I get c1 plus c2. And 0 to the derivative, -2c1 minus 8c2. We get, for example, that c1 is equal to -4c2. So -4c2 plus c2 is equal to -1. Therefore, c2 is equal to 1/3, and c1 is -4/3. Now, looking at this equation, let's just think about whether or not this makes sense. The object was hanging peacefully from the spring. Then the object was stretched downward by 1 meter, and it was released. Now, over the course of time, both e to the negative 2t and e to the negative 8t are approaching 0. So what we're seeing is that once the mass is released from the spring, it's sort of just immediately sliding back to equilibrium position.
If beta is greater than omega, the system is overdamped. In overdamped systems, the system returns to equilibrium without ever oscillating.
That concludes today's material. Today was day 1 talking about spring mass systems and differential equations as used to represent the movement of a mass attached to a spring.